video, I'm going to explain how to determine a rate law starting from a mechanism. So here we have a three-step mechanism for the formation of hydrogen iodide, and we want to know what is the rate law for this mechanism. So I'll explain to you a four-step procedure that will help you determine it. The first step is to identify the rate determining step. The rate determining step is always the slowest step. So what we have right here is two fast and one slow. So this right here is a rate determining step. We're just going to write that as RDS. Now the second step is to write the rate law for the rate determining step. So we're going to look at this step right here, and we want to write the rate law corresponding to that. So for this particular step, our rate law would be R is equal to, we have K3 and then H2I, the concentration of that, and we have iodine, I. The third step is to make sure that the coefficients are all fine for the order. So because we have a coefficient of 1 and 1 in here, the order right here is going to be 1. So that stays the same. So we can just ignore it. Now the last step of this procedure is the trickiest part, and is to recognize which are the intermediates and take care of them. So we want to substitute any intermediates we have, because what we have right here is the rate law only for the last step. We want the rate law for the whole mechanism. So by taking out the intermediates, we will be able to obtain that rate law. For this particular example, we have H2I and I, which are both intermediates. So we have H2I in here, and we have it here. So it's a product and a reactant. That tells you it's an intermediate. And then the same thing happens for our iodine, I, right here. So we need to be able to substitute those intermediates out. And the way we do that is by using the other steps. So we have this step right here and this step right here to substitute them. This is when our equilibrium arrows come into play. Notice that for the last step, we only have K3 as one arrow. But for step 1 and 2, we have K1 and the reverse step, K-1, and K2 and K-2. So we're going to use that for our advantage. So before I continue, I'm going to label this step number 1, number 2, and number 3. So let's start with step number 2. So this is our step number 2. As we can see in here, we have the equilibrium arrows with the K2 constant. So we can use that and say that because they're equilibrium arrows, the rate for the forward reaction, I'm going to call that FWD, is equal for the rate for the reverse reaction. And now we can write each of these. So we know that for the rate when it goes forward, K2 times I, and then we have hydrogen, H2. And for the case of the reverse, it's K-2 and H2I. And what matters for us right now is this right here, and that's what we want to obtain. So we just get the equation for it. So H2I would be equal to K2 times the concentration of iodine times the concentration of hydrogen over K-2. I'm going to leave this like this for now. I'll plug them in the equation at the end. So we can do the same for step number 1 to obtain the concentration of iodine. Let's do that. Like before, we have the equilibrium arrows, so we'll do the same as in the previous step. The rate forward is the same as the rate for the reverse. That will mean that K1 is times I2 is equal to k negative 1 times I squared, because we have this coefficient right here. This is what we care about, so we solve for that, meaning that our I squared, is going to be k1 times I2 over k negative 1. And this is the other part we were missing. So now we have iodine and H2I. And all we have to do is plug them into the equation. So this was the equation we got from step 3. This was the equation we got from step 2, and this was 1. So because we have in here I squared, we still can't plug that in here. But after we plug H2I, you'll see that we will be able to do that. So R is equal to K3. I'm going to substitute this H2I with the value of this one. So that will be K2 times I times the concentration of hydrogen over K negative 2 times another iodine that we had from right here. So these two will multiply each other and it'll make them squared, meaning that R is equal to K3 times K2. I'm going to put all the K's together over K negative 2 and put that in parentheses times I squared times the concentration of hydrogen. And finally, we can plug this in here. That will give us this. So this is what we get after we plug in the I squared. And we can put again all the K's together. We have K3 times K2 times K1 over K negative 2 times K negative 1. And then we have here hydrogen and I2, so iodine gas. And because all of this is K, meaning it's a constant, we can just change that to the K for the reaction and call it, let's say, Kr. So R would be Kr times H2 times I2. And that is the rate law. So as you could see, the step 4, changing the intermediates, is the trickiest part. But it just involves substitution. So thank you for watching this video. I hope you liked it and found it useful. And if you did, please be sure to give it a like and subscribe to see more videos like this one.